This evening, it's our great pleasure to welcome Prof Michaël Gillon from the University of Liege. He has an interesting background. He started out in the army, and then in 1998, he gave that up and started to study, first of all, biology and biochemistry at the University of Liege, and then physics and astrophysics, and ended up with a PhD from the University of Liege in 2006. Since then, he's been directing a research group working on exoplanets particularly, and has received a number of honors and awards. Most notably, I should mention the highly esteemed Franke Prize last year in 2021. I shan't go into the other prizes, but he was also nominated among the 100 most influential persons in the world for 2017 by Time magazine. Michaël, we're looking forward to your talk, and without any more ado, I hand over to you for your talk on exoplanets. Rita, you still need to switch off your camera, please.
Okay, thank you for the introduction. So may I share my screen?
Yes.
Can you see the slides?
Yes.
Yeah.
Perfect.
Amazing. So I'm pleased to be virtually with you tonight to talk about exoplanets and this fascinating domain of science that has emerged within the last 3 decades, as it is one of the most dynamic fields of modern astronomy. So since the beginning of the humankind, we are fascinated by the possibility of the existence of other worlds. And this question has been for a long time only theological, metaphysical, philosophical, but with the Copernican revolution, it started to become a scientific question. Already back in the time of, after Copernic, the Italian philosopher Giordano Bruno proposed that the stars were just suns, and they should be surrounded by their own cortege of planets. And at that time, it was, of course, not possible to confirm this claim, but centuries afterwards, it finally became possible thanks to the advent of modern astronomy. So before we detected exoplanets, we first start by having a thorough understanding and a thorough view of our own planetary system. So our solar system, now we know it very well. So it can be divided in 2 parts. The inner part of the system is composed of 4 terrestrial planets, rocky planets, mostly composed of a core of iron and a bit of nickel, surrounded by basically rocks, silicates. And further out in the system, you have giant planets that are much, much more bigger, much more massive, and especially the gas giants, Jupiter and Saturn, that are, well, Jupiter is more than 10 times bigger than the Earth, is 300 times more massive, and it's basically a big ball of hydrogen and helium with a small core of maybe up to 10 Earth masses. And then further out, you have the ice giants that are kind of third Jupiter-like planet. So they have a core of rocks and ice, and they are also enshrouded within a big envelope of gas, hydrogen mostly, but it's not as big as Jupiter and Saturn. And then in addition, of course, you have plenty of small bodies, asteroids, comets, that are basically the remnants of the formation of our planetary system. And we know the system very well, and we know that our world is really unique in this system. So what makes it so special is if we are focused on life and habitability, is really the existence of water in liquid form on its surface. So in astronomy, we call the terrestrial planet that has liquid water on its surface an habitable planet, which is a badly chosen term, but still this is the one that we use. And if you look at the content of water of Earth, it's only 0.02% in its bulk composition. So it's close to nothing. But this is really what makes our world so special, because it makes possible, it's one of the main ingredients of life. All cells, all living cells depend on water and are composed mostly of water. It's a main constituent of life. So by extension, when we say we're searching for habitable worlds outside, well, in the universe, we are first searching for places where we could have liquid water. And if we look at our solar system, intuitively, it's easy to understand that if you go too close to the sun, the irradiation of a planet is too high to make possible the existence of water in liquid phase. And if you go too far, it's just too cold and the water will freeze. So you can easily define intuitively, but in practically it's a bit more complex, what is called an habitable zone. So it's a range of distances for which you could have, in theory, liquid water on an Earth-like terrestrial world. And if we do the computations, and if we look at our solar system, we see that, of course, Earth is within the habitable zone, but also Mars falls close to the outer edge of the habitable zone, within the habitable zone. Venus is a bit too close. Mercury is way too close to the sun. And the example of Mars shows us that it's not enough, of course, to be within this theoretical concept of a habitable zone to be habitable. Now that we have dreamt about the existence of life on Mars, of complex forms of life on Mars, for decades, but now we know very well that Mars is kind of a dead planet. It has nearly no atmosphere, and we know it had some liquid water on its surface, but within its first billion years, and it has lost its atmosphere, and it's probably related to the fact that it has also lost its magnetosphere, which was protecting the atmosphere. So as Mars is a very tiny, low-mass planet, 10 times less massive than the Earth, it has less internal energy, and it could not sustain a magnetosphere for long. And without magnetosphere, the winds, so the charged particles emitted by the sun, and also the X-ray and UVs, had an easier task to erode the atmosphere. And once you lose the atmosphere, of course, you cannot have liquid water on the surface. Venus is the opposite example. It has an atmosphere, but it's way too dense because Venus had passed through a phase of what is called runaway greenhouse, because it's so close to the sun, well, closer than the Earth. The irradiation was too large, and the water of Venus from the surface, but also a large part of the subsurface water must have been evaporating and then was photolyzed. And what remained was oxygen reacting with the carbon, forming a very dense atmosphere, very rich in CO2, 10 times, well, 100 times more dense than the one of the Earth. So clearly not habitable worlds, our two neighbors. And if we look into the solar system, there's no other place like Earth. So we really have to target the stars, which are much further away. And it's something really to keep in mind here, is that the typical distances in the solar system can be expressed in, let's say, thousands of millions of kilometers. When we talk about distances between stars, we talk in light years. The nearest star is at 4 light years away, and it's 1 light year is 10,000 billion kilometers. So the distance range is orders of magnitude larger, and it's clearly a distance we cannot, of course, travel across with our current technology. We have to use what we get from this system, which is only the light coming from the stars, or maybe the planets. So at the time of Newton, they were also already considering searching for exoplanets, as surprising as it could be. Huygens made some computations, and they were really bad in terms of potential of detection. And so this field of searching for exoplanets remained something that was pure speculation, basically a kind of fantasy for centuries. But then at the end of the 20th century, it became something really serious, and notably thanks to the coming of the Hubble Space Telescope. So Hubble did not detect directly exoplanets, but in the 80s, when it was targeted towards very young stars, it could show that these stars had circumstellar material around them. And this is something that was predicted by the theory of formation of our solar system, which is that when a star forms, it is basically by collapses of a big cloud of gas and with some dust. And you have the central part of the collapsing cloud that is going to become a star, thanks to the high pressure, temperature, making possible nuclear fusion. And the rest of the material will form a disk by conservation of angular momentum. And this disk, this is supposed to be the place where planets are formed. So by extension, if we consider that all stars have the same origin, they should also be, when they are young, surrounded by this kind of protoplanetary disk, I will call them, and it was confirmed by Hubble. So this was a demonstration that the conditions to form planets were existing elsewhere in the universe. And then came the 90s, and well, there were a first exoplanet detection in 1992, but around a very weird star, a pulsar, which is a neutron star, so a dead star, basically. So it was not such a big mediatic and even scientific result, because the nature of this planet is still a bit poorly understood. But then came 1995 and the first detection of a planet around a sun-like star. It was achieved by these two Swiss astronomers, Didier Queloz and Michel Mayor, using a telescope in France, basically, in the Observatoire de Haute-Provence. And it was a huge surprise because what they discovered was a giant planet like Jupiter, but super close to its star. So the orbital period, so the time it takes to complete an orbit for Jupiter is 11 years. This planet is 4 days. So it's totally scorched, baked by its star. And this is something that was not predicted by the theory based on the formation of our solar system. In theory, you should not be able to form planets so close to the star. But it was confirmed. And it was awarded by a Nobel Prize three years ago. And this was really the origin, the birth of a very dynamical field of astronomy. At that time, there were only 2 teams, one Swiss team and one US team that were competing to find the first exoplanets. And they were kind of considered crazy people trying to do so. But when the community understood that it was possible to detect these exoplanets with current technology, then many projects were funded and arrived. And then you had a huge, well, progressive, but nearly exponential rise of the number of detections. So what you have here is the year, and you have the cumulative number of detections. So starting in 1995, there's 1 planet. And now we are at 5,000 exoplanets that have been discovered by more and more ambitious projects. And with this huge harvest, we can draw important statistics. And the first one, which is certainly the most profound one, is that planets are everywhere. Basically, nearly all stars in our galaxy, and by extension of the whole universe, are surrounded by planets. They are the natural byproducts of the formation of a star. But, and this was not at all predicted, and this is what is so interesting, is that these planetary systems are very diverse, much more diverse than what we could expect based on our understanding of the formation of the solar system before the exoplanet revolution. For instance, you have on the upper left here, you have the illustration of a system which contains 6 planets of a few Earth masses within the orbit of Venus. So this is a sun-like star, a kind of sun twin, but it has a very complex system, very compact system, very different from our own system. And we now know that this kind of system are found around 30 to 50% of the sun-like stars. We also know that our system, our own system with something like Jupiter at 5 Earth-Sun distance from the Sun, is pretty rare. We know that it's at most 5% of the sun-like stars that have a system like ours, a twin of our solar system. We have this Jupiter very close to the stars, Jupiter-like planets, so we call them hot Jupiters. You have planets around binary stars. Sometimes they orbit one of the member of the binary. Sometimes they orbit the whole binary. You have planets on very elliptical, eccentric orbits, not like in our solar system, where the planets have circular orbits, nearly circular orbits. We now know that there are hundreds of billions of planets that are free floating in the interstellar void, and a few hundreds have been detected. And these planets, we know that they must have formed in a protoplanetary system, so in a protoplanetary disk, and they should have been ejected by gravitational interaction with other planets. Because the formation of planets is super efficient, you form easily planets of very different masses. And when they encounter, when they are too close to each other, one of them can be kicked out of the system. And you even have planets around dead stars, so neutron stars, white dwarfs, and these kind of things. So it's a very interesting zoo. And we now have a theory that explains well why we could detect these planets so close to their stars. So this theory has been, well, let's say, confirmed by complex hydrodynamical simulations that were made possible thanks to the improvement of the computers, basically. And in this simulation, it is shown that when you put a massive planet within the protoplanetary disk, which is mostly composed of gas and hydrogen, it interacts by gravitation with the gas, and it forms waves of densities that you can see on the left here. If the planet is not very massive, this is the only thing that you would see, basically, with this kind of structures. If the planet is massive enough, it's going to clear completely its surrounding. So it's going to accrete the gas or repulse the gas, and you will have a gap within the disk. And in all cases, this interaction with these huge structures, these density structures that have their own mass, important mass, is going to make the planet basically exchange energy and angular momentum with the disk, and it's going to make it move. And generally, it's going to migrate inwards. This is something that could have happened even in our solar system. That could, for instance, explain why Mars is so small, maybe because Jupiter get closer to the Sun and then get in the other direction by an interaction with Saturn, if you believe some computations. And these gaps in the protoplanetary disk, they are not just the fruit of our imagination. Thanks to the advent of new instruments, we are able to see them directly, image them directly. So what you have here is a real image of a protoplanetary disk, and you see plenty of gaps here that should be the traces, the direct traces of planets that are forming in this disk. So it's really fascinating. It's a real image. We are really able to witness the formation of planets. And within these thousands of exoplanets, there are a few that are particularly interesting if you're interested, like me, in the possibility of life elsewhere in the universe, because these planets are low mass, close to the mass of the Earth. They are as small as the Earth or even smaller, and they orbit within the habitable zone of their star. So in theory, they could have liquid water on their surface, and why not host a biosphere? So the next step in this quest for habitable worlds is to study in detail this planet and search for traces of life. And this is not an easy task, of course. The most intuitive way to do it would be, of course, to take a huge telescope to be able to make an image of the star with, in the image, also the planets, to resolve the planets from the stars and to analyze spectroscopically the light coming from the planets. But this is really challenging. What you have here is a real image on the left of what is called brown dwarf. So it's a failed star, a star that is not massive enough to sustain nuclear fusion. And close to it, in 2005, was detected an object of which has a planetary mass, but a few times the mass of Jupiter, clearly not a terrestrial planet. And on the right, you have the best case so far, the most fascinating result obtained by direct imaging. So by really taking images of the star and seeing the planet close by, you have 3 planets of a few Jupiter masses close to, well, not close, far from a star, a young star, which is more massive than the sun. And you see on this image that the star is blocked, is hidden, and it is due to the method that was used to detect this planet. I'm going to explain it afterwards. So if we could get this kind of image in which we see not giant planets, but terrestrial, potentially habitable planets, then we would be in a very good position, because we could just spread the light of these planets, do spectroscopy, and look in the spectra of this planet for chemical signatures of different molecules that could maybe indicate a photosynthetic or at least a biological activity on the planet. So if we do this, so if we observe in the infrared, which is of course a wavelength range where you have the most crucial molecular information about the planet, if you do this for Venus on the top, you have a really strong signature of CO2 at 15 microns. For Mars, it's the same, because Mars has a very scarce atmosphere, but it's dominated by CO2. The amplitude is not the same, of course, of the signature. And for the Earth, in addition, you have signature of you have a more complex spectrum with signature of water and ozone. Ozone is the byproduct of the photolysis of oxygen. Oxygen coming from photosynthesis. So it's could be a clue to get to the conclusion there is something going on this planet, and maybe it's of biological origin. And here I want to illustrate, but here I'm talking to chemists, so you know what I'm talking about. I want to illustrate the fact that life is interacting with its environment, and it modulates its environment, including the atmospheric composition of the whole planet. So thanks to the advent of photosynthesis and after the big oxygenation of the surface and the oceans, you had the oxygen level in the atmosphere that rised. It was also modulated by some geological events, but nevertheless, it's clear that photosynthesis was the cause of this rise of the oxygen level, which started something like 600 million years ago, and which reached now a value of 20%, while it was only a few percent before. And this is what we want to achieve for this exoplanet, is to study the atmospheric composition and find traces of what we call a chemical disequilibrium, which would indicate that there is a very strong source of a given or several given molecules that could be related to metabolism that we know here on Earth, and that could indicate, if we have no other explanation, that there is life on these planets. But imaging an exoplanet is something really difficult, and I want to illustrate this with this firefly here on my lighthouse. So if it is kilometers away, I should be able to detect it and to image it if I have goggles that are powerful enough. It's just a matter of the size, the power of and the resolution power of the goggles. But if I turn on the lighthouse, which is orders of magnitude more brighter than my fireflies, and this firefly is totally lost in the light of the lighthouse. And whatever the resolution of my Google, I won't be able to detect it, because here we are really facing not a problem of resolution, but a problem of contrast between something that is very faint and something that is very bright. And this is exactly the same situation for exoplanets. They are light years away, so they are very, very faint. And furthermore, they are angularly super close to something much brighter, the star. So a solution, which is something that on which plenty of teams are working on, is illustrated here by this natural example, which is a full eclipse of the moon in front of the sun. When you look at the sun, you don't see its outer atmosphere, what we call the corona is not visible. It's a pity, because it's a very nice structure, this corona, but it's not visible because of the much brighter disk that hides this structure. But when the disk of the sun is hidden, then you see the corona in its full glory. And so the principle, which is a basic concept behind what we call a coronography, and the name comes from the corona of the sun, is to use an optical device that is going to nullify the light arriving at the central focus of the telescope, of the instrument that you're using to see the neighborhood of the point that is blocked. And so here is an illustration of what could look a space mission able to make image of an Earth twin and to study spectroscopically the Earth twin, which would be light years away. So this is something that several teams are working on now. So it is a space telescope that will have what is called a star shade. So this is a kind of, let's say, artificial moon that will go thousands of kilometers from the telescope with a precision of a few microns in terms of position, radial and longitudinal position. And this star shade will block the light from the star, will making possible to see the surrounding of the star and to detect the planets and to image them directly. And unfortunately, this mission will not exist before, I would say, 20, 30 years. It will cost a lot, and we are not there yet. Nevertheless, we don't need to make direct image of exoplanet to detect them. If you look at the first exoplanet that was discovered, it was detected by a method which is called radial velocity method, which is illustrated here. So on the left, you have the Earth, on which we have our telescope. On the right, you have the star, and the planet you don't see the planet, but we can look at the spectrum of the star, and because the star is orbiting the center of mass of the system, so when we see the planet is orbiting the star, it's not exactly true. Both are orbiting the center of mass of the system. So the star itself has a small, very tiny orbit, which make, if you look the radial motion of the star, it makes, by Doppler effect, it makes the lines of the star move to the red, to the blue, to the red, to the blue. And so by measuring extremely precisely the spectra of the star, you can measure this Doppler effect, and you can measure the radial velocity of the star, and you can, from that, detect the planet indirectly, just by the influence, the dynamical influence it has on its star. And the amplitude of the motion of the star will be directly dependent on the mass of the planet. So you can infer the mass of the planet. Thanks to this method, about 700 exoplanets have been discovered. And then there is a much more powerful method, further, which is based on another phenomenon. Again, this is an indirect method. And this method is basically a shadow method. So it's illustrated here. So when you have something that is invisible, you can still detect it by its shadow, like this invisible hand. And more concretely, if you want an illustration of the principle of the method, you can look at this nice image, which show what is called a transit of Venus. So The Earth is the third planet in the solar system. All planets orbit within the same plane, the ecliptic. So the two inner planets from time to time pass in front of the Sun as seen from Earth. And so we can make this kind of nice image. You can see how small is Venus compared to the Sun. But for exoplanets, we can use the same principle to detect them. And the way to do so is just to measure the brightness of the star. So we can make an image, a resolved image of a star, because it's too far away, and we just see them as point source. But we can measure the brightness, and we can do it extremely precisely now, especially from space. And when the star is eclipsed by one of its planets, it will appear a bit dimmer, because a part of the light emitted in our direction is blocked by the planet. And so we will have a drop of brightness. It will be periodic. So every orbit, we will have one drop of brightness. So we will be able to infer the period. From the period, we can infer the distance to the star. And from the depth of the amplitude of its transit depth, we can also infer the relative size of the planet. Oops, something happened. Can you still hear me?
Yes, yes, Michael. Yeah.
Yes?
Yes.
Yes, yes, no problem. We can continue.
Hello?
Oui. Michael?
Can you hear me?
Yes.
Yes.
Okay, I'm going to assume yes, it is the case. Okay, now this method, the transit method, it has been very powerful to detect exoplanets. It has detected something like 3,500 exoplanets. But in addition, it makes possible to study the atmospheric composition of the exoplanets, and notably during the transit. So when the planet passes in front of the star, there is the annulus of the atmospheric limb of the planet that will pass in front of the star too. And as it's not totally opaque, it's going to filtrate a tiny fraction.
Attends.
Try and get Michael back.
Voilà. Michael? Michael? Yeah.
Yes. Can you hear me now? Because
Yes.
I've been disconnected at some point. Or
Yes.
Yeah.
okay.
We can start from the measuring the brightness of the star.
Okay, so can you still see my slide or not?
Not
yet.
Okay, so where is Teams? That's weird because I don't see any option to share. Okay, here maybe. Sorry about this.
Don't worry.
If I do this, no, not now. Not yet, huh?
No.
It's not the right screen that has been shared. This one?
Yes, perfect. Yes, great.
Okay, good. Sorry about it. So I explained you this transit detection method. It has led to the detection of most of the exoplanet, but it also enables the transit configuration, so which is a particular geometrical configuration. You need the orbital plane of the planet to be well aligned compared to the observer. It makes possible to study the atmosphere of the planet itself. Because when the planet passes in front of the star, you have the atmospheric limb of the planet that is going to pass also in front of the star, and it's going to filtrate a tiny fraction of the light emitted by the star in our direction. So by doing spectroscopic measurement outside transit and within transit, we will see small differences that come from this filtration. And this is how we are able to study the atmosphere of transiting planets, to measure their composition. And we would like, it has been done for giant planets. We would like now to do it for habitable, potentially habitable exoplanets. Of course, it's much more challenging. And the reason it is challenging is the size question. Because here, to illustrate the difficulty, you have Venus in front of the Sun. So Venus has the same size as the Earth, so it illustrates well the problem. Imagine the tiny area that is hidden by the planet itself of the disk of the star. It's only 1/10,000 of the disk area. This is the amplitude of the transit itself, of the drop of brightness. But the amplitude of the signature of the atmosphere will be much, much smaller because the area covered by the atmosphere is way smaller. I'm talking about the atmospheric limb here. So it's much less than 1 part per million, which is basically undetectable because the Sun is so big compared to Venus or to the Earth. So the solution is to go for smaller stars. And fortunately, most stars in the universe are much smaller than the Sun. And the most interesting are called ultra-cool dwarf stars. They are very frequent in the galaxy, in the universe. They are about twice colder in surface temperatures than the Sun. And they are also much smaller. They are about 10 times smaller in radius, so 1,000 times in volume. In fact, they are as small as Jupiter. And if you put an Earth-sized planet in front of them, if you make the computation, then the spectroscopic signal from the atmosphere becomes detectable. Detectable, but you need still to be in space, and you need a very big telescope operating in the infrared. And so far, this kind of telescope did not exist, but now it does. It is called the James Webb Space Telescope, and it has been in preparation for 20 years, from the basic idea to the launch. So it has been a long drive to make it happen, but now it was launched by NASA, ESA, and the Canadian Space Agency at the end of last year. It's a 6.2 meter telescope, so the diameter of the mirror is 6.2 meter. It is a segmented mirror. It is covered by gold because gold is very reflective in the infrared. Because this telescope is an infrared telescope. It was first designed to study the faintest and most distant galaxies, but it turned out to be a very amazing instrument to study exoplanets too. And so this telescope is a real scientific but also technological achievement because it is so big that it does not fit within a rocket. No rocket can take it to space when it is deployed. So they had to deploy it, to fold it within the Ariane rocket, 5 rocket, and they had to deploy it in space. And it was something that was never done before. So it was very stressful. It took weeks to have the telescopes deployed and months to have it fully operational. But now it's totally operational and it works within specs. So since a few months, we have now this facility that makes astonishing observation of the universe, including of exoplanets. But we have the telescope, but we also need projects that are able to find the best targets for this James Webb Space Telescope. And so we need projects that search for potentially habitable planets around nearby ultra-cool dwarf stars, or at least very small stars. So in terms of ultra-cool dwarf stars, the only project that is efficiently searching for planets around this kind of tiny stars is Speculoos. This is a project led by Liege. It is done in collaboration with several other institutions. And it is using a network of robotic telescopes spread all over the world. Well, there are 4 in the southern hemisphere in Chile, 1 and soon 2 in Tenerife, and 1 also in Mexico. And we have a sample of 1,400 stars that we are surveying, monitoring with our telescopes. in search of this transit of potentially habitable planets. And then in the US side, there is a project which is a bit complementary. It is a space-based project using a satellite which has 4 lenses. I wrote telescopes, that it's not really telescopes. It's lenses that are coupled with camera, wide field lenses that are observing basically the whole solar neighborhood, so the 200,000 nearest stars, searching for transits. It should be able to detect planets a bit more bigger than the Earth in front of stars that are up down to 15% the size of the Sun. So basically, it can't monitor stars as small as speculoos, but it can monitor stars that are a bit bigger and detects planets that are a bit bigger than the Earth. And it has been in operation since 2018, speculoos since 2019. But speculoos started effectively in 2011 with a prototype. We needed to do a prototype basically to get the funds to fund the speculoos. And we used our telescope TRAPPIST. So it's a Liege robotic telescope that we installed in 2010 in the Atacama Desert of Chile. And in 2011, I decided to devote a fraction of the time of the exoplanet program that I was leading on TRAPPIST to do a prototype of speculoos. So I identified 50 nearby ultra-cold dwarf stars, and I decided to monitor them one by one with TRAPPIST. And in 2015, big surprise, in our data, we saw this signature here on the right. So what you have here is, as a function of the time, is just the normalized flux of the star. And you can see there is a drop of brightness that was monitored during one of the nights during which we observed the star. On the left, you have the position on the sky of the star. It is in the Aquarius constellation. Doesn't mean anything, but still, it's nice to show the Aquarius constellation. And this system revealed to be really fascinating because we were sure there was one planet. We confirmed it with other observations, and we saw other transits. And at some point, we understood that there was many planets in this system. Notably, at the end of 2015, we were observing the second inner planet of the system, a transit of the second inner planet, using a big telescope. It's a VLT telescope, so very large telescope, which is in Chile, an 8-meter telescope. And we call this event. So what you have here is the evolution of the brightness of the star measured by the telescope during the night again. And you see there is a big drop of brightness and a small one, and there is an increase and another increase back to the normal flux level. And the only way to explain this is that 3 Earth-sized planets space in front of the star basically at the same time. And 2 were unknown to us at that time. So we gathered in 2016 plenty of observation of the system. We knew that there were 4, 5, maybe 6 planets, but we could not really crack the system with our ground-based observation because of the limited precision and because of the night-day cycle and so on. So we asked NASA 3 weeks on an infrared telescope called Spitzer, which is a small but powerful telescope. It's no more in operation now. And during the 3 weeks of observation that were granted by NASA, we had 34 transit events. And thanks to this observation, we could really crack the system and show that there were 7 planets around the star, and they were all very close to the star. So here is an illustration of the system. You have 7 Earth-sized planets. The range of distance, the distances, of course, are not to the right scale to the star and between the planets, of course, but the range of sizes of the planets is correct, and also compared to the star. So all of them are basically Earth-sized planets. And if we look now at the habitable zone of this star, it is super close to the star because the star is very faint. So the fainter the star, of course, the closer you have to be to the star to have the right amount of photons reaching the planet to make possible water to be in liquid phase. So this habitable zone here has a range of orbital periods that goes from, let's say, 6 or 5 days up to 15 days to be compared to our Earth orbit of 1 year. So it's really very close to the star, and still in this system we have nearly four planets that fall within the habitable zone. Two that are a bit too close to the star, but still quite temperate in terms of irradiation, and one which is a bit too far from the star to be potentially habitable, but still also quite temperate. And if we look now at the scale of the system, it's really amazingly compact. So the distance between the inner planet and the star is 1% the Sun-Earth distance. The outer planet distance to the star is 6% the Earth-Sun distance. So within this tiny space around the star, you have 7 Earth-sized planets, which is totally unique and totally extraordinary. And in fact, the distance between the planets, the adjacent planets, is only a few times the Moon-Earth distances. So they are really, really close to each other. And here, just to illustrate how close they are, if you could be on the surface of one of these planets, this is an artistic view here, you could see the star in the sky much bigger than the Sun, because the planets are so close to the star. Let's say 10 times bigger than the Sun, depending on the planet. And also the planets themselves, you would see the planets like you see the Moon, basically. So you would see the clouds, the structures, whatever there is on the surface, if the clouds permit, you would see it. Well, in our solar system, we see other planets, but we see only basically a point of light. You need a telescope to be able to resolve a bit the planets. And also because this star is so cold, it emits mostly in the infrared and a bit of red. So no blue light at all here. There is no blue light that would be scattered and making the sky blue on this planet. The atmosphere will basically you would see very well the stars in the sky even in full day, and the star itself would be reddish in the sky. And also because the distance between the star and the planet is so small, the planet should be what is called tidally locked. So because of the tidal influence of the star, they should have been trapped in a configuration where they always face the star with the same hemisphere, like the Moon to the Earth. So you could have very weird climates where you could have a very hot day side, a very cold night side, and maybe an area in between which would be more temperate. Of course, it depends on the atmospheric properties. If the atmosphere is dense enough, you could have an efficient heat transfer for the day side to the night side, and then the thermal contrast will be much smaller than in this specific case. Also, the star itself, it's not at all a Sun-like star. It's much smaller. These kind of tiny stars evolve much more slowly than a Sun-like star. And so the lifetime of a star like TROPIST-1, so we named the star TROPIST-1 after the discovery, the lifetime of this star is something like 1,000 billion years, while the Sun has a lifetime of around 10 billion years. And it is because the pressure and temperature in the core of the star are much smaller than in the Sun, so nuclear fusion is active, but it's very slow. It's much less efficient than in the Sun, so this makes much less energy release, but in the same time, the lifetime of the star is much, much longer. And it also means that this kind of stars, our universe is 13.5 billion years old, all these tiny stars are very, very young compared to the final lifetime. So they are still in the early phase of the evolution from a magnetic point of view. Also, they are very active. They have also a fully convective structure, which makes the magnetic field very complex. It's always disconnecting, reconnecting the lines. And so you have plenty of what is called flares. So surface explosion, chromospheric explosion, which emits a lot of X-ray, UVs, and probably also charged particles, which make maybe the life of the planet very hard because they receive a lot more X-ray and UVs than the Earth because they are so close to the star. It could make the atmospheres evaporating very efficiently. So maybe they are not so habitable, but maybe also they have a large reservoir of volatile elements that could replenish the atmospheres, and they basically would have a metastable state for the atmosphere that would still be long-lived. Anyway, we don't know if they have an atmosphere, but we could know, and this is what made this system so amazing. And so when we discovered it, NASA was fully enthusiastic. The whole community was fully enthusiastic. They had plenty of press release saying it's the best target for James Webb, and it is really the best target for James Webb in the terrestrial regime. This on the right below here, you have a simulation of measurement to be achieved, to be done by James Webb, observing the transits of the TRAPPIST-1e, I think, so one of the planets in the habitable zone. And it shows that with enough observation, we should be able to detect molecules like water, CO2, methane, ozone, and we could maybe relate them to some biological activity. It will require a lot of observation. Of course, we need the atmosphere to be there, so if there's no atmosphere, we will detect nothing. But it means that we have at least the capacity to detect this atmosphere and to study their composition. And by the way, you see this kind of measurements. What you have here is a wavelength and the x-axis, and the y-axis is the size of the transit. Because when the planet atmosphere is more opaque at a given wavelength, the planet looks a bit bigger in our measurement because light is blocked by the atmosphere. So if the atmosphere is rich in CO2, at the wavelength corresponding to CO2, the planet looks a bit bigger because light emitted in our direction do not pass within the atmosphere. Well, outside the CO2 band, it passes, and so the planet looks a bit smaller when we measure its size. So this is what we call a transit transmission spectrum. Yeah, I wanted also to outline how crazy it was, this system, the discovery, not only from a scientific point of view, but also from a, let's say, cultural point of view. We've seen this system in science fiction novels, in video games, in comic books. We have been in contact with plenty of artists that are really fan of the system, and it's really something very special for us astronomers to see our discovery going out in the world, even through imagination, and to be taken by this artist and to be reimagined by this artist. And in the meantime, we read these books, but we still go on with science, of course. And now we have Speculoos that is fully funded. We have these 4 amazing telescopes in Chile, which are much bigger than TRAPPIST, much more expensive too, of course. So they are also in the Atacama Desert, which is the driest place on Earth. It's 2% humidity, high altitude, nearly no clouds, nearly no turbulence, perfect place for astronomy. We have one at the Teide Observatory, and a second one is coming, and one in Mexico. And after 2 years and a bit of problem with the COVID, we finally detected a first system that we announced a few weeks ago, which we call Speculoos 2, because Speculoos 1, we keep the name for TRAPPIST-1 also, because it was discovered by the prototype. So you have here the first transit that we call of a potentially habitable planet with Speculoos. Oops, sorry, Speculoos 2c. And you have here an illustration of the system to show how compact it is compared to the solar system. There are only 2 planets to our knowledge in this system and not 7, but still it's an interesting system. So they are all both very close to the star. And you see the orbit of Mercury here, and you see how small are the orbits. They are both a bit bigger than the Earth. One is too close to the star to be habitable. One is at the inner edge of the habitable zone. And in this diagram, what I show is the flux, the irradiation of the known terrestrial planets, exoplanets. And here you have the signal along the y-axis, the signal that is predicted in terms of atmospheric characterization for these planets. So the larger the signal, the easier it is to study the atmosphere, basically. And you have also a color code as a function of the signal to noise with James Webb. And you have on the top of this diagram, you see all the TRAPPIST-1 planets that are really the best target for James Webb. But this new system here, Speculoos-2, it has also another name, more archaic, let's say, LP8909, is also a very good target for James Webb. And with Speculoos, we hope to detect a few dozens more planets. Now that we are, let's say, on the right path to discover more planets, our survey is now fully operational. TESS is going to discover also other interesting planets. But this James Webb ultra-cool dwarf, let's say, exploration is not the end of the story for a study of exoplanets and search for potentially habitable worlds. Within the next decade, we will have giant telescopes on the ground that should be able to detect maybe potentially habitable super-Earth by direct imaging around nearby stars, around a few nearby stars. So you have here an illustration of what is called the extremely large telescope, which is in construction in Chile. It's a European telescope, and its mirror size is 40 meters. So it's a segmented mirror. It is composed of something like 1,000 small mirrors. It's really something amazing. This telescope, the optics will be able, the mirror will be able to change its shape as a function of the turbulence of the atmosphere to correct in lifetime the turbulence to get the sharpest possible images. But it will take time to have it work, but it's in construction. And I mentioned you that there are some space-based mission concepts that are developed now, and within maybe 2-3 decades, one of them could exist and should be able to detect maybe hundreds or at least dozens of Earth twins, so Earth-like planets, which would be in orbit around not ultra-cool dwarfs, but really sun-like stars, and to study the atmospheric composition. So I would conclude by saying that for centuries, we have speculated about the possible existence of other worlds, and this question has become scientific with the Copernican revolution and the advent of modern astronomy. But now we are really in the era where we are getting closer and closer to a possible answer. And this is really a very, let's say, exciting and fascinating time to be astronomer, because I mean, we are getting close to a really fascinating answer to this fundamental question. And I thank you for your attention, and I will be happy to answer all your questions.
Thank you very much indeed. And now we will look across for questions. Yes? You have someone? No.
So can you raise your hand? Yeah, okay. Mike and Joe.
Go ahead.
Sorry, I forgot to unmute my mic. Would there be any value in building a James Webb of a massive scale by using, by building it in space, using the space station to build it outside the atmosphere, so you don't have the launch problems, and you could build it basically as large as you like? Would this be a feasible thing to do?
Well, it's clear that we are limited still by the size of the James Webb Space Telescope. If we could have a James Webb Space Telescope 10 times bigger, then it would become really, really interesting in terms of what we could do. So I think it could make sense, yes, indeed, to have a modular telescope, and that would be assembled in space. To my knowledge, there is no project in this sense, but that's an excellent suggestion indeed.
Can you name it after me?
Yes, sure. with pleasure. If you find me the funding, we will do it together.
Yes, I know that it was very complicated to calibrate the James Webb. Did it really succeed fully with all the different mirrors that they were lined up correctly?
So the the alignment of the mirrors was just perfect. In fact, the optical quality of the images is even better than expected. So there was no problem in this alignment. Of course, it has been very stressful, but there was no problem. Now, in terms of calibration, because all the instruments that are out there in space behave a bit differently than in the lab in terms of yield, efficiency, noise, and so on. They are fighting to get the best possible calibration, but it does not impact at all the exoplanet studies, because all we make is always relative. In fact, we don't need absolute flux measurements. We always basically compare the signal to itself. We compare the signal within the transit and outside the transit. So we don't need absolute fluxes. It's something that is really critical for the study of the first galaxies, for instance, to infer the distances, the age. But for exoplanets, it's not a problem at all. Nevertheless, they are making huge progress on these calibration issues, and I think it will be no more a problem within a few months.
Has it been hit by any particles in the space? And is that a problem with the large size of it?
No, it was expected that it would be regularly hit. Here, the micrometeorite that collided with it was a bit bigger than expected, that the distribution that they assumed, but still it made no issue. No, there was no failure due to the hit. And it was maybe an outlier. They think it was just an outlier, basically, that most of the impact will be of much smaller particles, and normally it will not make the system age more quickly than they were expecting.
Thank you.
We'll see.
Other questions?
Mike and Joe.
Yep.
Mike?
Yes.
Sorry, I keep muting my mic. At the present moment, you can see, well, you can work out the atmosphere of a planet as it transits its sun. Do you foresee it? Well, and that has to be quite a low percentage of the possible planets, because they're not all on the same orbital plane. And yes, a lot of planets are not going to go in front of their sun. Is there any way, first of all, to detect them, and secondly, to be able to analyze their composition or whether they have an atmosphere or not?
Yes, so there are other ways. So the transit method is for the transit configuration make things easier, but indeed it's a low probability geometrical configuration. So most of the planets do not transit. So there are other ways. There is a direct imaging method that does not need a planet to transit. And also we can do what is called high resolution Doppler spectroscopy. So basically what we do is we observe the system in very high resolution, spectroscopic resolution. And we have, in fact, the line of the planet that are moving relative to the line of the star. And so what we can do is to correlate a template of a given molecule, let's say CO2, with the spectra, and we will be able to detect this motion relative to the global spectrum of the system. And it has already been done for giant planets, and in theory, with the ground-based giant telescope, we should be able to do it for a few nearby systems for a few terrestrial planets. So it will make possible to detect some molecule and study to measure, to infer the abundance, thanks to this technique. I don't have a lot of time to explain it, and I should also illustrate it, but it's also something that works pretty well.
Harry?
Thank you. An excellent talk. I really enjoyed it, although I'm an organic chemist, so there was a lot of things that I didn't know. But then I have a question, which is a chemist's question. You explained that you can basically detect the composition of the atmosphere, but I want to go sort of one step further for life. you also need metals for catalysis. Is there a way of detecting what's the composition of the planets themselves? What kinds of metals there are, and can that be detected? Because it's the metals that actually catalyze the reactions, the chemical reactions.
No, what we can do is to measure, to detect the metals in the stars themselves, and we can make the assumption that the metallicity of the star reflects the initial condition of the formation of the planet. And so a metal-rich star should have a metal-rich protoplanetary disk, but you can think about, you can imagine some special cases. If you look at Mercury, for instance, it is super metal-rich because it's a remnant of an impact. So basically, it's a core. Mercury is so small because it's the core of a terrestrial planet, and all the rocks have been ejected by an impact. So what remains is basically a big ball of iron, Mercury. So, and this kind of stochastic event, of course, we cannot predict them, detect them. Else, for the metals, what we can do is to measure super precisely the density of the planet. So for TRAPPIST-1, we know the density with an amazing precision of the planet of a few %. And then we can compare to our structure models for terrestrial planet, and we can get some constraint on the composition of metals, of silicates, and of volatile elements with some degeneracies, but still we have some constraint. And so we can infer maybe that it's more iron rich than the Earth or less, but it's very limited, of course. What we would need is in situ measurement, and we're not ready to do this.
X-ray spectroscopy, could that be helpful?
X-ray spectroscopy is something that could be useful to study the exosphere of the planet. So you could have some absorption in X-ray of a huge envelope around the planet. So what is called an exosphere is basically the upper atmosphere that is eroded and goes in space beyond the gravitational field of the planet. And it can form a kind of big cloud around the planet, and it's only light elements, mostly hydrogen. And so in UV and maybe in X-ray, it could be detected. For giant planets, it has already been detected, this kind of exosphere of hydrogen. And for terrestrial planets, it has been attempted. For TRAPPIST-1, we tried in UV, but we failed to detect it. But unfortunately, also this kind of tiny star is very variable in X-ray and UVs because it has plenty of flares, emission, and so it's really difficult to get precise measurement in this high energy wavelength range. But it's also very interesting to measure the star irradiation in X-ray and UVs because it tells us the environment, the radiative environment of the planets. We can get some constraint on the survival of the atmosphere in this condition and so on.
No more questions. I think we could draw the meeting to a close, and thank you once again, Michaël, because that was a very, very clear presentation, very interesting presentation. And thank you once again for your clarity. And we look forward to following the development of speculoos in the near future. I wish you all the best for your research in that area. Thank you once again. Remind the members that our next meeting is in November when we have David Leigh from Manchester. And with that, call it a day. And thank you once again. And I'm glad that you were able to receive our appreciation ahead of the meeting. So enjoy.
I like them a lot, and my son likes them a lot too. So thank you very much.
Thank you, and thanks to everyone for joining. Have a nice evening.